So you registered for math analysis. Does anybody here know what it is? Any idea what you registered for? No? Well, it's required, right? Well, what you really registered for is, once you look at it from high enough altitude, would look to you pretty much like calculus. What you're doing here is pretty much calculus. So, but calculus on a much, much more theoretical level and much more general, right? Because there are different calculus. There is complex analysis, there is functional analysis. The word analysis, nobody ever bothers explaining what analysis means, analytic techniques mean. You kind of roughly know what they are, but I think what they mean is taking limits, essentially, right? So you're studying things that involve limits. Pretty much like Calc 1 limits, but maybe limits over sequences of functions, right? Or limits over complex rather than real numbers. So in this class, it's going to move so slowly that you would not notice it. It would not look to you too much like calculus, because what we're going to build is just the principles of mathematical analysis, right? The principles, in other words, just the very basic layers, the very, very basic ideas of... Yeah, sure, go ahead. All right, so where were we? So what we're going to study in this class are just the very, very basics, the building blocks to understand all the type of analysis, right? Every analysis that you are going to lead on a higher level will assume what we're doing today, what we're doing through the semester as given. So that's all we'll have, unfortunately, time to build. We're not going to delve very deeply into the calculus, into the functional analysis, into all the other things on which this class is, on which they are all built on this class, so to speak. So to illustrate what must be done, let's say, what are we going to do for the first week? One thing that you don't bother in calculus is to really examine what you're doing in calculus, really. What in calculus you're considering functions of a real variable, right? Functions that are taking real numbers and giving you out real numbers, right? But the first important question is, what are real numbers? Because the answer to that will influence the particular theorems and the particular things that are true in that particular region. Whereas, so for instance, let's begin with this basic question. So the first very, very basic question, let's see how you would answer this. What is the cube root of 1? All right, what do you think cube root of 1 is? Yeah. Are you done, guys? No, good. Somebody is not done, right? Somebody is already, right? Yeah, so any suggestions? Anybody would like to tell me what is the cube root of 1? 1. Wonderful. So one person is saying 1. So let me write 1 here. What else? Anything else?
2 more.
Huh?
2 more. Yeah, 2 more cube roots.
Oh, okay. Wonderful, right? So one person is saying there are 2 more cube roots of 1, right? So that actually depends on the context, right? So you see, cube root of 1, in calculus, the answer is 1. But in complex analysis, the answer is there are 3 solutions. The other answers are minus 1/2 plus I root 3 over 2. And minus 1/2 minus I root 3 over 2. Right? There are 3 answers. So it's very important to understand what those things mean to begin with, right? What is it saying? What am I saying when I say cube root of 1? What am I saying when I say cube root of 2? Right? How many solutions will it have? Will it have any solutions, right? The other answer is that you might not have any solutions. Depends on the context. If we're dealing with the rational number line, there are no, well, there's going to be 1 here. But if I say I take the square root of, let's say, 3, this is nothing. There is no square root of 3 in the rational numbers, which we're going to try to understand today. So you see, so all those things, they are meaningless unless you specify in what type of structure you are asking those questions. Hello?
Is this 509?
Yes, what is the course? Huh?
Spanish?
No, it's not Spanish. There are a bunch of other 509s there. And say nobody wants to come for analysis, only for Spanish. Is it for Spanish or for analysis? Huh?
Analysis?
Please sit down. All right. So the first overview, I actually am not going to mention much about it since I don't have too much time. So constructible numbers. You might have heard about things like that from another class. So maybe abstract algebra, it's considered briefly. But you see, in analysis, the very first thing we have to do is undergo some sort of study of numbers. What do we mean by a number? So this is a brief description of what was more or less thought to be a number during the time of Pythagoras or later. It's not really a reconstruction of history, but it tells you some things that the ancients at the time of Pythagoras knew. So they knew how to construct numbers. They, for instance, multiplied numbers not like we multiply them. They multiplied them geometrically. Right? So if you're interested, I can tell you how it's done. Here's basically a description of how you can consider a product of the numbers a and b, geometrically. Right? What they used to do is they had something that was a piece of rope. Right? So it's basically just a piece of rope that you can stretch, and using this thing you can draw straight lines when you stretch it. Right? And they would peg this rope, and what they could do with this rope, they could also, with a peg, they can draw a circle, right? So the very basic geometric constructions used to be done with what they call straight edge and compass. And using a straight edge and compass, you can multiply numbers. You obviously can add numbers. Adding numbers, you just take one piece of rope and extend it by another piece of rope. That's addition of numbers, right? And the pieces of rope that you create, those are the numbers you constructed, right? The way you construct a number would be, you can take a piece of rope and you can cut it. The way you would cut it is perhaps, for instance, if you have two circles intersecting that rope, or where they intersect, or where the circle intersects the rope, or you can just cut it, right, where you obtain a point. But all of this is can be described a little bit in the notes on constructible numbers. One other really impressive achievement is that they could actually take square roots of numbers, right? If they managed to construct the number a, they would be able to take the square root of such a number. And that's describing that construction. Well, Spanish? It's around 12. Are you taking Spanish?
No.
Analysis?
No.
So where we will begin is with the Pythagorean assertion, all is number. Has anybody ever heard this expression, all is number? What might they mean when you say all is number?
Everything could be described by numbers.
Everything can be described by numbers. Yes, that's actually a very, very good explanation. So everything can be described by numbers. They thought of it geometrically, right? So when they say that, I mean, to begin with, what did they know? What did they develop very well? Geometry. So when you have, just take a piece of line, right? This is one piece of line. And take another piece of line. Those pieces of line are segments of space, and there is a relationship between them. Right? Now, how would you describe the relationship between them? Right? So that they're not just kind of different types of space altogether. They are just pieces of space that you can understand once you understand what is a small piece of space. So what you can do is you can take something that you can call a unit. In other words, just take some measurement and just arbitrarily call this 1. Right? And then what you can do is just take this 1 and just measure how many times this number 1 will fit in this line segment, right? So in other words, you were able then to describe, that's what they hope to do, to describe this line segment in terms of the unit, right? In terms of a small piece of space, you describe a larger piece of space or a smaller piece of space. In essence, you just need to understand this piece of space to explain everything about all other pieces of space. But in that construction, they would have a finite algorithm. In other words, this construction will have to terminate. So, in other words, perhaps this is just sticking a little bit out. So what you can do is you can cut it into smaller pieces, and eventually you're hoping that the end result is going to be some integer plus a fraction. So in other words, an integer plus a fraction of this one unit of space. But then Pythagoras or his disciples, they discovered the following type of number. It came exactly from the Pythagorean theorem. So they discovered something that looks like this. Suppose that we take, I just blew it up, but we take a unit measurement, 1 and 1, and we create a right triangle with this unit measurement. And then we have this, I'll call it C. So then you would like to try to communicate the size of C in terms of the unit 1. What do you know? You know that 1 squared plus 1 squared is equal to C squared. So C squared is equal to 2. Right? Because 1 squared plus 1 squared is just 1 plus 1. So we have that the square of this number is equal to 2. So what are we searching for? We are searching for a number whose square gives you exactly 2. So here is an interesting proposition. I'm actually going to prove something more general than just 2, but let P be an integer and P is prime. So you all understand what this means. It's a natural number, so it's a positive integer, and I'm taking a prime number. So for instance, 2 is a prime number. Then there is no number m over n. So in other words, there is no fraction of integers such that m over n squared will give you p.
Where m and n are integers?
Where m and n are integers. We'll just use any integers, right? Where m and n are integers. So you understand, right? When the Pythagoreans said O is number, they meant that you can take a length of space, and using that length of space, you will be able to communicate precisely any other length. In other words, you can communicate any fraction of space in terms of the one fraction of space that you know and call 1. proof. So suppose that we found m and n whose square is equal to a prime number. So without loss of generality, the greatest common divisor of m and n is 1. Because if whatever this fraction is, I can cancel out common terms and write it in simplest form. And then we have greatest common divisor of m and n is 1. Okay? That's without loss of generality. So what does this mean? This means that m squared is equal to the prime number times n squared. And that implies that the prime number must be dividing m squared. The prime number divides m squared. You agree? But a prime number has a very nice property that you see it divides m squared, which is m times m. The way a prime number is truly defined is that if it divides a product, it must divide one of the terms of the product. So the implication is it either divides m or it divides m. Right? For instance, 4 is not like that. Right? 4 is not a prime. If you take 4 and you want to divide 4 into 4, right? So 4 can be written as 2 times 2. So 4 doesn't divide 2 and doesn't divide the other 2, but it divides the product. But with prime numbers, this is the case. Prime divides m and m. So that implies that the prime is indeed dividing the number m. And what does this imply? This means that m is written as prime number times some integer k. And that implies that m squared is equal to the prime number squared times k squared. Right? And what do we have here? We have prime number squared times k squared, m squared. Well, that's the same as prime times n squared. Agreed? What does this imply? This implies that, well, we have two factors of p, right? P is raised to the second power. So one can divide p and the other will have to divide n squared. So that implies that the prime number divides n squared. Which in turn implies that the prime number divides n. That's a contradiction, right? Because we said that m and n have no common factors. But what we have shown is that m is divisible by p and n is divisible by p. That's because greatest common divisor of m and n is equal to 1, and p divides m and p divides n. So that's the contradiction. Wonderful. So what's the fuss about? Right? Just very technical, and what we have shown is that no rational number. A rational number is what Pythagoreans consider to be a number to begin with, right? Because by this geometric scheme, you just you must have them you must take this unit and just construct the number, and constructing means finite process. So the fuss about it is that what this seems to be showing is that there is no such number c. number C satisfying C squared equal to 2. In other words, what they were really surprised by is that this is not a number. You have this stick, but this is not a number. So why is it such a big crisis? It's such a big crisis, actually, that the person that revealed the secret, revealed that there are constructions of that form. His name, I think, was Hypatius of Metapontum. He was drowned as a punishment. Right? That's funny, right? They actually pressed him under the water and killed him like this. For what? For this thing not being a number like the Pythagoreans thought. So let me try to explain to you why this might be important. You have this? Can I erase?
I understand that proof, but how does that show that there is no such number such that C squared?
Because if you assume there is such a number, you are led to a contradiction, right? So the assumption of such a number implies, based on fractions, that you have m over n, which you simplify to they're going to be relatively prime to each other, right? So you simplify it; they are relatively prime to each other, and then if you continue with the proof, you actually then say that they are not relatively prime to each other, right? So you have this contradiction that they must on one hand be relatively prime to each other, on the other hand they cannot be relatively prime to each other.
But that's assuming that C is some number m over n, which assumes that C
Yes.
is a rational number.
But then the question is, what would be an irrational number, right? So there is this term. If you label something, you dismiss it, right? You say, oh, it's an irrational number, right? And you dismiss it. But what the hell is an irrational number? Obviously, I cannot claim that I explained to you what is a rational number, but at least that seems to be making some sense to us, right? Some sort of sense, because, well, I ask you, measure the length of this table, right? Measure the length of this table. So you take a stick, here's a stick, right? And you go like this, and then like that, and then like that, and after, if you're very meticulous, maybe it will take you an hour, right? If you're less meticulous, maybe a bit less time, but you will finish, and you will give me the answer. But imagine I actually was mathematically precise, and I said measure this table, and whatever number you give me, I tell you you are not done. It's incorrect. It's not the length of the table, right? You did not communicate this length precisely. Now it seems you understand what I'm saying, right? Because let's say this unit does not fit a finite number of times. It does not fit 10 times or any fraction amount of times into the length of the table. So you never actually communicate the precise length. So in the next example, I'll try to explain to you why that might be important, right? So it seems, okay, who cares, right? So you give me an approximate length, and you are done. But approximations have some sort of bad quality. So I actually had to explain this example. It's a bit bloody, and the reason it's so bloody is I had to explain it to people in pre-algebra, and they were bored to death, right? Right? They were bored to death, and they enraged me enormously. So you don't care about approximations, right? So this number C, you can say, well, it's not a number of the form m over n, right? Well, and in general, we don't really care about it. So a very simple thing that would then happen if you don't care about whether or not root of 2 exists, right? Basically, you know that if you cheat a little bit, you would say that C is root of 2, right? That expression, as I already mentioned, it's a bit meaningless, right? Because what is root of 2? In complex analysis is one thing. In some other context, it's not meaningful at all. In real analysis, I mean, you are so used to writing root of 2 as the solution on your exam. But what are you saying? You are saying that unique number whose square is 2. But what do you mean by that? So suppose this discussion is just annoying you, and you don't care about it, then. And you don't care, I mean, just say, okay, give me a ruler, I can measure the length of this table, everything will be wonderful, I'll give you some sort of number, and, you know, if you don't like this number, you can go to hell, right? Okay, then you don't care if I drop a brick on your head. Because, you know, here is a brick, it's a very heavy brick, and we can do the following experiment. So, let's say I'm going to leave this brick just for safety, so it's enough, just 5 feet over your head. So there's enough time, right? So this brick is going to be lifted 5 feet over your head. I'm going to drop it. Right? And when I'm dropping it, then the question is, what's going to happen to you? Right? Well, let's analyze this precisely. So the position at time t of the brick is given by 16 t squared, where 16 is 16 feet per second squared. Right? That's from basic physics. Okay? The next question is, what's going to happen to you? It's a big break, trust me, right? I will not scheme on that. And if you want, I'm not sure if I can obtain one, but maybe I can borrow one from platinum or what is a very heavy material? Maybe from gold even, right? It's pretty heavy. It's a simple question, no? Yes, please?
I guess it depends on how much time you have.
Well, what do you mean by that? Exactly, how much time do you have?
Well, you could calculate it by either setting like the initial position of the brick at the origin, or like the top of your head as the origin. You could calculate technically the amount of time you have, and either to the amount of time you have before the brick hits your head, or hits the position of where your head
Well,
is.
that's very nice. I like what you're saying. It's very mathematical, right? To understand what happens to you, you're gonna calculate the following, right? You can say you can make the following postulates, right? If brick, did I spell brick correctly?
Mm-hmm.
Thank you. Contacts head, then you die.
You know that for sure?
Well, I can make it very certain by selecting a very heavy brick, right? That would then be very certain. I mean, this I think would suffice to a degree, right? But if necessary, if you are not happy, I'll select a bigger brick, right? Depending on how thick is the skull, right? So if brick contacts head, then you die, and that's one assumption. And the second assumption is time of death. Is equivalent to moment of contact. Again, I'm simplifying a bunch of things naturally, right? But if you make them, if you just describe the same problem on more sophisticated level, the problem is still the same. Trust me, it's still the same. Time of death is moment of contact. You agree? So let's calculate what's going to happen, right? So then what you have is a moment of contact is going to satisfy the equation 5 equal to 16 t squared. You agree? 5 is equal to 16t squared. So that is equivalent, if you continue solving this, then you are going to say t is equal to root 5 over 4. You agree? But root 5 is not a number. We just showed that there is no such number like root 2, root 5, root 7. Those are roots of prime numbers, right? But this is not a number. Or if it is, you have to then communicate what it is, right? Then, what does it then mean if it's not a number? Which implies no moment of contact. Which implies no moment of death. Right? Or it might, I'm not saying that that's the only conclusion you reach, right? Well, you like approximating things, right? So let's say take root of 5 and take the root of it, right? Just take it in your calculator. Your calculator is going to spit a bunch of values, right? So that's what people always tend to write on the exam. They always simplify a root of 5, especially if they take calculus or pre-calculus, right? So let's just see, shift root of 5. We get 2.236067978. Except, is this root of 5? No, right? This is not the moment of contact, right? This is an approximation. That's when you're saying, well, let me find a number that kind of gives me a number. When I square this number, I get something that looks like 5, but not exactly 5. But if it's not equal to 5, then if it's a number below 5, the brick is then over your head. If it's a number past 5, the brick is already in your head, right? But at no moment of time did the brick ever smash your head, right? So either of those things you then have to do. Either you did not die from the brick, and therefore I cannot be accused, right, for dropping this brick because I did something completely irrelevant, right? This is not cause and effect, right? I cannot be accused in a court of law for killing you because you died spontaneously for no clear reason, right? There was just a brick floating over your head, and then you're dead, right? Which you deserve for not studying analysis, perfect, right? Or you just don't die, and therefore you're immortal, right? There is no reason that you should be afraid of. You have the superpower, a very thick head that survives any impact. So that's one crisis, right? And that's why they were so worried about it, because their entire wonderful theory, they kind of imagine you spend your life, you're eating beans for a living, right? That's what they also believe in, right? Eating beans, for whichever reason, right? Or not eating them, no, actually not eating them, right? I always get confused about it, right? I think they were afraid of beans. Yes, that's the thing. I think they were afraid of beans. I don't know exactly why, but they were, right? So you do all this weird thing, and then suddenly you realize that your religion, or Pythagoras, or whatever it is, it's a false prophet. Whatever you believed in is completely wrong. So then, of course, you're going to kill somebody who is going to expose you.
What about square roots of numbers that are not prime, like square root of 6? Like that doesn't.
That actually is also going to be irrational. You can prove that as well. Not a hard proof, right? As soon as you have a number, the more general proof, which I just did not need to for this illustration, is that as soon as you have, if you just take an integer, and you find its prime factorization. As soon as one of the prime numbers is not raised to an even power, that's already going to be an irrational number.
Okay.
Irrational number, again, is a word, you should understand, right? We did not explain what irrationality is. We did not explain why it should be a number. We just showed that our basic idea about just taking measurements fails to work. That's really what we are showing, right? Our basic idea of taking measurements fails. So there's another example that I found a bit amusing, and actually that's exactly how I came out. It was Providence, I think, that led me to this problem. I was switching channels, and so I was switching channels, and you know the show Ice Road Truckers? Yes? Ice Road Truckers. I never watched it, but I stopped for that one moment because something interesting was going on. And what was going on is a dispute. So there was an officer giving a ticket to this trucker for speeding. But there was no radar, there was no evidence at all, direct evidence, right? that he was speeding. So I understood from this discussion that he did not measure him with a radar speeding, but he gave him the ticket. So I tried to understand how that is happening, and I wrote it in this particular lecture. So I thought of it this way. So suppose that the initial position is at 0, and the final position is 60 miles away. So in other words, here is this road, and the truck is driving on this road. And suppose that the speed limit is 55 miles, right? Now suppose that there is a camera here, so there is a station A, and there is a camera in station A, and station B, a camera at station B. So the tracker was recorded to be at position 0, exactly at 12 o'clock. So in other words, we can represent 12 o'clock as 0, right? P of 0 is equal to 0, where P is the position of the tracker. And P of 1 hour, so in other words, it actually took him 1 hour. P of 1 is 60. Right? So, question, if this was the condition, was the tracker speeding?
Yes.
Interesting. So let's take a poll.
Well, I guess we don't know if his rate was constant the entire time.
We don't know anything. All we know, so understand this question, right? So nobody is there to see what he is doing in between position A and position B. All we know is that there is a road, presumably he was on this road, and that at 0 hour, he was in 0 position, in place A. And at 1 hour, he was 60 miles away from that position. And we know that the speed limit was 55 miles.
Along the entire road.
Along the entire road, for simplicity, right?
Yeah, so yeah.
Yeah,
It
for
had to
sure,
be
at
at
some
some
point he
point.
was speeding. Yeah.
Interesting, at some point you're saying. So, we'll see.
Was this the case in the show?
Huh?
Was this the case?
This is the case in the show, right? But I guess a lot of people noticed the same thing. I mean, I recently saw, I mean, it should be obvious, I suppose, but I once saw an animation. I thought one of my students did it, but no, it was actually done before I even gave this lecture, right? So I guess a lot of cases, independently, you come to this conclusion. And interestingly enough, that independently, several people use the same tools that I did, right? So let me try showing you, first of all, let's try to have a poll. I want to know how many people are going to be, if you're a jury, are you going to convict him? So speeding, and what should we say, another not enough information. So in other words, innocent until proven guilty, right? And don't let your emotions rule. Which people in America all the time, they do that, right? I actually told the people this thing about Scott Peterson, and they stopped me. Who is Scott Peterson? I thought, wow, you're so young. You have no idea, right?
Who's Scott Peterson?
Exactly. Oh, you don't know, right? So there was a trial, of this guy who killed his pregnant wife, right? I mean, the situation, as far as at least I could see that from the outside, reminded me of the book The Stranger. You know, you ever heard of the book The Stranger?
Albert Camus.
Yeah, precisely, by Albert Camus, right? So this person was convicted, but Albert Camus was convicted not because of what he did, but because he did not cry at the funeral of his mother, because of a bunch of other things that people found odd and unpleasant, and they do not relate to him, basically, right? So in this trial, I mean, I don't know, I mean, everything was very, very circumstantial. So the pregnant wife disappeared already. I mean, likelihood is, you know, who wants her to disappear? The husband, right? Likely, right? But there is no, I mean, nothing that was presented there at all gave any evidence that he did it, right? So, I mean, if you go through the technicalities, at least from what they released, maybe there was some more information, but from what they released, it appeared that there was no reason to convict him. Oh, everything was very circumstantial. No, there was no evidence that he was at the place of the crime. A bunch of things were not really established, right? But they convicted him, and the penalty is death. So very similar to Camus, right? I mean, if you can research this thing, and maybe I'm wrong. Maybe there was more evidence, maybe less evidence. But basically, maybe he's guilty, but there was no direct evidence.
How long ago was this?
I can't remember. Maybe 10 years ago, maybe more. Right? So anyhow, so going back to our case, right? You are very emotional here. Do you like truck drivers? No, right? So that's why, I mean, they're rude. I mean, you know, they're rude. They're obnoxious sometimes. So you think, well, they don't deserve to live. Especially very soon, they're going to be smart cars, right? So you don't need them as much. So how many think that he was speeding? Raise your hand. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11.
Well, what do you mean by that? The whole time he was speeding?
I don't know about the whole time, that he actually deserves the ticket.
Should he get the ticket or not?
Yeah, should he get a ticket or not? Okay, raise your hand again. I'm sorry, let's do the count. 1, 2, 3, 4, 5,
I don't know.
6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Wow, overwhelming majority are willing to convict him, right? It takes only one jury, right? There's also a movie, 12 Angry Men. I can also be part of it, right? So I think it takes only one member of the jury and the person is dismissed. How many are going to try to say he's not guilty? Not enough information. I cannot convict him just yet. One person. Just one person is willing to listen to the situation a bit longer.
I also don't. I don't know if there's not enough information, but I don't think you can convict him of speeding. But I don't know. If
3 people, I see. Oh, okay. So one person, you see, with his courage inspired already 2 other people, right? But then there are others that sit there and just don't care. All right. If he was speeding, why was he speeding?
Because if he wasn't speeding, he wouldn't have made it 60 miles.
I don't know what he would have or wouldn't have, right?
No, if he didn't go over 55 miles an hour, he couldn't make it 60 miles in that 1 hour. So he had to at one point go over 60 miles or 55 miles an hour. For sure.
But you're saying perhaps is, you know, somewhere there is something correct there, but to me it sounds like this. To me it sounds, well, he's a gentleman. Why? Because if he were not a gentleman, he would not be wearing a hat or something like that, right?
Oh,
but there's no...
Like if I was a cop and he sped for like 10 seconds, I would be like, all right, you're not gonna get the ticket. But if you're saying, did he speed? For sure he sped.
Well, let's say it's categorical. We are kind of in Germany, so there is no such thing as for 10 seconds. As soon as you are speeding even for 1 moment, you deserve the ticket, right?
Yes.
Germans are like this, by the rules. Die Regeln sollen genau befolgt werden, right? That's what the Germans would say, right? The rules must be followed to the T. Yes?
Yeah, but isn't that, the first time I heard this example, easy pass, was in Calc 1 for the mean rule.
Yeah, I mean, I actually present this because I actually wrote it at the same time for both Calc. No, it actually was written for analysis, but it's very parallel, so I presented it in Calc 1. Yeah, mean is actually it's good there, but okay, go on.
Okay, so assuming that this driver uses maximum legal speed for the entire time that he was driving, he would make it at P0 he would be at 0, and at P1 he would be at 55.
But it's very interesting. I like your argument. It's really nice, right? It's very nice. You can be the prosecutor, right? Yes. I really like your argument, and I think what he needs now, that's his only chance, is to have a Jewish lawyer, right? Thank God, I can be of assistance, right? All right. So let me. What you said is the maximum speed. I really like it. Let me rephrase it a little bit. I don't know about the maximum speed. It's all very dangerous things. You know, we're assuming we know too much about velocity and about position and about all those things. We're assuming a lot of things here, right? Let's not assume too many things. So what can you say? Can you say anything about his speed? Let's say that, right? To convince the jury, we need to first, in my opinion, in my humble opinion, say something about the speed of the driver, right? Because I mean, is he like driving 1,000 miles an hour, or is he driving, 2 miles an hour? What is he doing? What can you say about his speed? Tell me something about him. Yes.
I mean, we also, you're saying that he reached the 60-mile marker in an hour.
Yes.
But what part of the truck? If it was the front and the truck is like 5 feet long.
Let's say that's not ambiguous. Let's say the middle, right? The middle of the truck was at 0, and then the middle was at position 1 at 60, right? Let's say this is not a problem, but that's a good marker.
It's a Jewish lyric comment.
Does it also
You're already
matter?
beginning though, right?
Does it also matter what his initial speed was? Because he might have been like slowing down.
But we don't know his initial speed. All we know is that in this moment, we just there was a photograph taken of him, so we know he was in station A at time 0, and then he appeared in station B at time 1.
I would even argue that initial speed is not relevant at all. Because even if he was starting at 0, he would have I would have to have time to accelerate to reach 55, but he would still be less than 55 miles in the.
Now, what you argued in terms of the maximum, I actually like this idea. Pretty smart idea, but still dangerous because we then talking about we're assuming too much about speeds. I think, right? I'll try to show you afterwards.
But why can't we assume basic physics in this example?
I don't know. That's the thing. I mean, it's very hard to know what we can or can't assume. Just a second. Yes.
Yeah, I was thinking. Suppose he had to stop 10 times at a red light, 3 minutes each. That's a half hour at 0 speed. So that means he has only a half hour to reach 60 miles. So he's definitely.
But you see, you're using your experience. You see, I mean, you're walking on the street and you know that the ground is hard, right? So you don't want to believe that the ground would suddenly open up, right, in front of you and swallow this person. So it swallow you, right? You trust in certain basic things. So we are right now in a very important court, not just a court of our peers, but in a mathematical court. Just a second, and I'll be with you.
This is assuming that it's continuous, and he's going on he's constantly on that line, that there can't be a jump from one place to the next.
Interesting, right? Continuous. It's another dangerous word, but good, right? We're then trying to, okay, but none of you yet, I think, told me how bad was his speeding, what was his speed, or at least some sort of indication of any sort.
Because you don't know, that's the whole point. The fact that, like the brick example, you know that the brick is going to hit the guy's head.
But I don't know that.
Exactly, which is why you could never convict that person of murder, which is why you can't convict this guy of
You
speeding.
see? Thank you, right? So when I kill all of you by bricks, right, one person is going to be having my back at least, right? I'll keep you alive for
I'm Jewish.
Okay, I will try again with this problem. So this is like, I guess you can use it, I guess, if you like take a function. I know I can see how this is used for average speeds and how you can use this example to explain this. When I say you remember when I said maximum, this is useful if you assume like average maximum speed, because between these 2 points, this driver could be driving 0 at 0 miles per second. He could be driving at 70 miles per second.
per hour.
Miles per hour. Yeah. Okay. Maybe. Yeah. But the actual variations in the speed are in a greater scale irrelevant, because it tends to one number, which is the average.
Okay, well let's go to the average, right? You mentioned the average. Before we go into those speculations, let's talk about the average. Right? And let's analyze that first. So average speed. There's also an interesting question, of course, why is it called averages? We'll get there, right? What is the average speed here? Right, so the average speed is position at 1 minus position at 0 divided by 1 minus 0. So change in positions divided by change in time. And the result is 60 miles per hour, which is bigger than the speed limit of 55. Right? So the average speed is bigger than 55. But now it's very important to understand what is average. How does it relate at all to what he actually did? Any idea? So what does this mean? Average speed.
We didn't have to necessarily go 60 miles per hour at all on a trip. But if you take all of his speeds together.
The summation of all them.
Well, that's actually very complicated. You are actually right, but you need integration theory for that, right? That's where the average comes in. So what is average when you have finite chunks? If you have finite chunks, it's one number plus another number, let's say, plus another number. Let's say we have three numbers, right? 3 speeds, and then we divide it by 3, and that's how we obtain the average, right? That's how average works on a finite scale, right? But there is a big difference between a finite scale and what would happen here, right? From your intuition, you know that it does not have to have finitely many speeds. Probably had infinitely many speeds, or one speed, right? Because of the intermediate value theorem, that if you change your speed, you have to go through all the speeds in between. Again, that's a major assumption, because that already assumes we are dealing with real numbers. We're going to study the intermediate value theorem and what it means in this class later on, right? So we cannot even use that. So let's try to just formulate something that we can use. Well, I would say that this is what average speed means. It means that if the tracker was driving at a constant rate, if he was not speeding up or slowing down, if he was driving at a constant rate, that rate would have to be 60 miles an hour. Right? But what objection can you make then? Right? We're saying that if he traveled at a constant rate, that rate had to be 60 miles an hour.
Because he didn't travel at a constant rate.
Yes.
If he didn't travel at a constant rate, he'd still have to go higher.
Well, that's speculation now. You're telling me what he would have to do, right? But I'm saying that, well, the direct evidence that you can see here, the direct evidence. The evidence tells you that if he traveled at a constant rate, that rate had to be 60 miles an hour. It doesn't tell you what would happen if he did not travel at a constant rate. That's what you're telling me. That's speculation.
Oh, and therefore we don't have enough information, and therefore we can't convince.
Well, there is one thing, right? So, one thing from calculus, right? So, there is a theorem in calculus, a very important theorem, by the way. And the theorem you remember as the mean value theorem, right? And what the mean value theorem tells you is that P1 minus P of 0 over 1 minus 0 had to be equal to P prime of some number T0. So let's interpret what this is saying. What the mean value theorem is going to say, in physics terms, is that if we calculate the average speed, the derivative represents instantaneous speed, right? So what the mean value theorem is telling us is that the truck, at some moment of time, at least one moment of time, had to travel at the average speed. You understand? So that gives us the direct evidence, or almost direct evidence through this theorem. It tells us that if he was traveling at 60 miles an hour on average, then there was at least one moment of time where that was his exact speed. Now notice the difference. Notice how dangerous it is to assume that, well, just speak about average, right? If I give one person 100 and another person 0, the average is 50, but not a single person receives 50. One received 100, another received 0. So you see? But here, it's another law of averages, where you have infinitely many things that you actually average. In that case, notice, the average must actually equal to one of the existing scores. You understand?
Yeah.
So that's what this theorem is telling us. Well, let's see if I can defend it. So the first thing we need to do is assumptions. So the defense is it's already something I haven't seen. Well, hopefully it's something you would understand later on. Assumptions that make this true, that justify use of mean value theorem. So the first assumption is that P of t the first assumption, let's say that t I should say P of t exists and is continuous for all t between 0 and 1. So let's understand what this first assumption means. Therefore, our first assumption is that this tracker had a position forever, from 0 to 60. He always had a position. You might think it's an obvious assumption. It's not obvious, right? One thing I cannot really tell you more about, but quantum physics, right? Yeah. That's one of the things that you at least heard, right? That you cannot determine the position of the particle and at the same time determine the velocity of the particle. So you can see that means that this is a big assumption that by no means is obvious. It's just something that you tend to believe from your everyday experience. So what we're saying is that he was located somewhere on this road, and his relocation from one point to another was continuous, whatever that means. It's a very big word that we're going to again try to learn precisely. Second assumption is P prime of t exists. For all t belonging to 0, 1. Can anybody explain to me what the second assumption means?
For the infinite amount of points between 0 and 1, the p prime, the average will exist at one point, right?
Well, p prime is not the average, it represents what? What's p prime of t?
The instantaneous.
The instantaneous, right? In other words, if you could install a camera inside of the tracker, instead of the truck, the camera will, if it's pointing at the speedometer, it would always record some speed. There would be a definite speed at any given moment of time through this hour-long trip. You see, so those are very big assumptions under which you convict this person, right? You're assuming that velocity always exists, and there's one implicit assumption is that you're assuming that there is a structure of time, that time is structured according to real numbers. That's a big assumption, right? So, and this assumption I could have actually just disputed. So as his lawyer, I hope I'll get a lot of money for that, but as his lawyer, here's what I could have done. That's something we're going to explore later on. It takes some time to understand this. You will not understand what I'm saying in some ways. So I drew you one line. And I drew you another line. Can you see any difference between those two lines?
No.
No, right? So, but now I'm going to label one line. Somehow, somebody told me that one of the lines is Q. In other words, it consists of only fractions. And the other is something we call R, real numbers, which we don't understand right now at all, right? Now, if you were an investigator and you would look at this line under a microscope and look at this line under a microscope, no matter how powerful is your microscope, you will not tell them apart. But there is a difference between them, a major difference. This is one thing when we're going to talk about different orders of infinities. This one has a much weaker order of infinity than this one. This line has some holes, but what are those holes? It's just some sort of weird word. You don't ever see any holes, right? There are no holes. But what I can do, but basically most of this line is mostly made of a vacuum, mostly made of empty space, which I'll try to communicate to you later on, right? So if I try to break it apart like this, cover it by segments that can be overlapping segments actually. And I measure the length of each segment and I add them up, the sum will be 0. In other words, what I can show, if he was traveling along this line, along Q, I can show that not only was he a model citizen and never tried to ever speed beyond 55 miles an hour, he in fact never moved at all, right? His speed was always 0. Or the distance that he was traveling was always 0. You understand? So that we will explain later on, and we'll cover that when we talk about infinities. I will be able to explain this argument more.
Did you get the ticket?
I'm sure he did, right? Because most of the jury, they don't bother, right? They just don't know average velocity, they don't care, right? But here is this picture. That's another thing that you can do with it. That's measure theory. That's already mathematics a bit more advanced, but you use it for integration. So this is a wonderful way of showing you that of proving that a person weighs nothing at all. Actually, exactly the same proof that showing that this line is of length 0, right? So this person, he just looks at him. He's very happy. He lost all his weight, right? And how would he prove that this person lost all his weight? Well, what you would need to do is you need to cut into many, many, many pieces, and then weigh them, those pieces, and then you see that actually all those pieces separately, they weigh less and less and less. So the sum of the pieces, the sum of the weights of the pieces does not add up to the total weight of the person. You understand? That's one of the crises that happens. I mean, you can look at it in several ways. You either look at it as the weakness of the particular number system that you are using, right? Or you can view that as a very profound philosophical or metaphysical problem.
So do you have to assume, are one of these assumptions wrong to be able to say that?
Well, I mean, you see, I can show you that the derivative will always exist, and there would be a continuous position. So the mean value theorem is true, and yet the conclusion, in other words, the hypothesis of the mean value theorem, the way I wrote them here, are true, but the conclusion is false. One thing that you are not saying here is that the mean value theorem is true for a structure called R. So the mean value theorem is true for R. And for this lower line, this argument that I drew above, I didn't even explain it, it would not work, right? So if you're using R and you cut the number into small pieces, that usual notion of length that you have is going to still hold, right? So if this is our number system, whichever that means, right? This number system will have to include roots of 2 and possibly many, many other things. What exactly it has to include, what exactly it is, I'll just even begin trying to explain to you, right? But you cannot tell those things apart. That's another thing that you should know, right? You cannot tell them by just looking at them. It's very hard to tell them apart. Certainly not under a microscope. You understand? So, if I'm to argue that we are traveling not on R but on Q, then the mean value theorem, its conclusion is false. In fact, I can show that the notion of distance is false. It doesn't work. Right? So that's what you do in analysis, right? It's sometimes a big problem. So if you do complex analysis, the mean value theorem is false for complex analysis, even though complex analysis has certain structures that real analysis does not have. Okay? So there are other examples. You can read more about it. I didn't illustrate the roots. There is also another example, which is the Fibonacci sequence. So another example is for, let's call it, communicating certain patterns. So communicating patterns, you all heard about the Fibonacci sequence. So the Fibonacci sequence is defined as the first term in the sequence is 1. The second term of the sequence is 1 as well. Do you know what is the third term of the sequence?
N minus 1.
Yes, it's the sum of the previous two, so that would be 2. The fourth term of the sequence is going to be 3. The fifth term of the sequence is going to be 3 plus 2, which is 5, right? And in general, the n plus 1 term of the sequence is the sum of the previous term and the one preceding the previous. Okay? So you have this sequence of iterations that calculate the Fibonacci sequence. Well, you can write a formula for the n term that does not use iteration, right? So you can actually write an explicit equation, and the explicit equation for the nth term. Notice we're only dealing here with integers, right? So we're only actually doing something in number theory. But the nth term here will be 1 plus root 5 to the nth power. So you see you have root of 5, right? You have something, you evoke an entity that we don't know what it means, if it exists or not. We know absolutely nothing about it. So that is the closed form that does not use iterations in describing. In other words, if I want to know what is the third term of the sequence, I just write 1 plus root of 5 cubed minus 1 minus root of 5 cubed divided by 2 to the power of 3 root 5. And if I assume this number exists and treat it as a regular number, I calculate and I get the number 2. All right. So in order to do rigorous calculus, you need to understand what real numbers are to begin with, right? If you're saying, well, what I'm doing, I'm considering functions over the real number line. I have to understand what is the real number line, what is making it distinct from the rational number line. So we have the following observation about rational numbers. So in algebra and in certain other subjects, you can actually, I wrote constructible numbers. Constructible numbers is really Q. You can construct any number Q, and actually you can construct also root of 5, root of 6, any root of integer can in fact be constructed. But real numbers are in fact even bigger, even more complicated than that. So if this is the number line Q, there is something missing. What is missing here, let's say, is root of 2. You see what I'm saying by missing? So what is root of 2? Root of 2 is a number whose square is 2. And we showed that no number of the form m over n can be that. Right? No ratio of two integers can ever be root of 2, so it's missing, it's not there. Right? So this is missing, but what I can define, I definitely have numbers whose square is smaller than 2, and numbers whose square is bigger than 2, right? Notice there is no root of 2, so I have to communicate it as saying numbers whose square is smaller than the number 2, and numbers whose square is bigger than 2. So this set is going to be A, and this set is going to be B. And let's write explicitly what A and B are. So A is going to be the set of all numbers R belonging to Q. I actually am going to restrict it to Q plus, in other words, only positive rational numbers. To avoid, because a negative square and a positive square gives you the same thing. So we have R belonging to Q plus, such that R squared is smaller than 2. You understand? I cannot communicate root of 2. I'm only dealing with rational numbers, so I have to communicate it in this form. So that's A. And we have the set B. That will be all the rational numbers in Q plus, such that R squared is bigger than 2. Clearly, Q plus is equal to the union of the sets A and B. You agree? Because there is no number that is giving you equality here with 2. So we either have a square of a number is bigger than 2 or smaller than 2 but never equal to 2. So question 1, does A have a largest element? No, that's true. Does not have a largest element. Let's see how we actually show that. So I'm going to first show you it's actually something like that is in Rudin, but I'm going to show you something that Rudin cannot write. Rudin is writing a pure text. In other words, there are certain things that you can mention as how you actually think about them, but they're illegal. You are not allowed to actually present this argument this way, because you're using entities that don't exist. Understand? Or you haven't shown that they exist. You know nothing about them. So here's what I do. So this is first is intuitive argument. So what I can do is I can write root of 2, and root of 2 is equal to r plus root of 2 minus r. You agree? Nothing changed. So what I'm doing is I'm just going to select any r in A. So select r in A. In other words, what do we know about r? We know the square of r is smaller than 2. And then what can we say? Then we can write this and say, well, this is equal to r plus, I can divide by the reciprocal of this number. Whatever, not what do you call this thing, but well, conjugate, right? Not the reciprocal by the conjugate, right? So we have 2 minus r squared divided by 2 plus, divided by, sorry, root 2 plus r. You agree? I wrote the same number. So root of 2 is still equal to this. You see what I did? I multiplied by the conjugate. So this is a minus b. I multiplied by a plus b, top, and divided by the same thing. So top and bottom. Now what I can do is, root of 2 is actually a number that is smaller than 2. So the entire result is bigger than r plus 2 minus r squared divided by 2 plus r. You agree? You see what I did? Pay attention to root of 2. Root of 2 is a smaller number. So what I now have is I have this fraction divided by a bigger number. Before 2 minus r squared was divided by a smaller number. Now it's divided by a bigger number. This is what you pay attention to. Okay? And look at it. We selected r in A. So we selected r in A, which means r squared is smaller than 2. So 2 minus r squared is positive, right? So the entire thing is r plus some fraction that is positive fraction. So the entire thing is bigger than r. Right? So you see, this is the intuitive argument, but you cannot look at it. I used root of 2, right? So what Rudin does, it doesn't actually show you how he comes up with this number. It just tells you the following. It tells you if, so that would be Rudin. If R belongs to A, check that S equal to R plus 2 minus R squared over 2 plus R belongs to A, and S is bigger than R. You understand? You are not allowed. You see what you are not allowed to? You are not allowed to use root of 2 because we haven't explained what it is. We don't know it exists or not, or any of its meaning. So that's why the argument is not present in root, among other things. So you can check that algebraically, right? You can just, you don't need to because it's a bit boring, but you can just square this number and simplify things and verify that this number squared is smaller than 2. And that's obvious if you just look at this. It's obvious that you should get smaller than 2 from this more intuitive argument. Okay? Intuitive but incorrect, not rigorous. But if you square this number S, you'll get something smaller than 2. And clearly this number is bigger than R because it's R plus a positive number. Good? When is this class over? 7:19. So let's do, so basically answer 1 is that the conclusion is that we can always pick a larger number, right?
What is
S
S?
is this number that I defined to be R plus this stuff in terms of R. In other words, what am I showing? The question was, does A have a largest number? How do you show it does not? Somebody said it does not. What you do is, well, pick any number and show that whatever number you picked cannot be the maximum. How do you show it's not the maximum? Find something bigger. Right? So I picked an arbitrary number R. And then I showed how to find another number that is bigger than R. And still in A. Do you understand? So conclusion, A has no maximal element in U plus. I'm going to leave the construction to you, but I'm going to write the second question. Question 2, does B have a smallest element? And the answer, what do you think the answer is?
No.
No. You verify that it's not. No. Verified. So I want you to try to construct an argument, right? So it's very astute, this observation. This is something known as Dedekind cut. Is that this is actually he discovered what was the actual problem with the rational numbers. And the problem is that sets of that form don't have a largest element, right? Don't have an element that is going to be blocking them from above, right? So they're kind of without boundary, right? They're spilling out, right? So A is spilling out towards something where you should have root of 2, and B is spilling in the other direction, right? So there must be something there to block it. Okay? So the set A does not have a definite ending. That's the intuitive feel for that. Right? Yeah. All right. So I don't think we should continue since next material will require a longer presentation. But you're welcome to prepare to read the lectures ahead of time, and make sure that you are looking through the homework already from the start. Right? There are homework on my site. It's solved. Don't be tempted to look at the solutions before you tried it yourself. For the exam, you'll have to try it on your own.